What it do, YouTube? I've been sitting on this one or procrastinating recording this video for a little bit, so we're just going to get right into it. Welcome back to another topic review. Today we're going over Module 27. If you are new to this series, new to the channel, I am a student at the Flatiron School, which is a fairly popular coding bootcamp. If you're unfamiliar with it, I'm currently in phase 3 of 5. I'm getting pretty close to the end of the phase. There's 31 total modules, and this video is on number 27. So we're really close to the end. I tried a different kind of format for this vlog series in the last video, and I didn't really like it because it went on for like 45 minutes. So I learned a little bit from that. That might have been part of why I was procrastinating a little bit, because I was kind of pontificating on how I would record this next video. So I'm kind of going back to the old method, and I'm just going to give you like my sort of synopsis of what I learned in the module, as opposed to the last video. What I did was I took the learning objectives directly out of each lab that I did, and I in my own words explained what the learning objectives said, like you will be able to explain or something like that, right? Took freaking forever. So I'm just going to kind of give you the broad strokes and like sort of tell the story of Module 27, so to speak. Yeah, of course, as always, I don't do this on behalf of or for Flatiron. I will be using some pictures and some code snippets from the curriculum in Flatiron, so just disclaimer there. If you want to see like the notebook or the labs or anything that I'm doing directly, it's all available on my GitHub, as well as like other students' GitHubs if you look around hard enough. So yeah, I'm not doing this for Flatiron necessarily. This is a documentary of my learning experience, but all credit for code snippets and the cool PNG photos and stuff like that goes to Flatiron. So without further ado, let's get into today's vlog notebook. So all of Module 27 was reviewing or introducing the idea of decision trees, which broadly speaking is a particular type of classification algorithm. So the last couple of videos I've been discussing mostly logistic regression as a classification algorithm. Now, logistic regression is a binary classifier, right? So it classifies data points into basically yes or no for like a given question, or null hypothesis, perhaps, if you want to think about it in like a Bayesian sort of way. So decision trees can classify things into 2 or more categories, is one of the major distinctions between decision trees and logistic regression. It should also be noted that a lot of times you hear the word decision tree or phrase referring to a lot of different types of tree algorithms broadly, but we're going to talk specifically today about decision trees and regression trees, and I'll talk a little bit about like what the difference is there. But point being, like casual conversation, decision tree is just like kind of used as an umbrella term. But when you're talking about specific types of models, if you're in like a technical conversation, you should keep in mind that decision trees and regression trees are 2 different types of tree algorithms. Of course, they're used to more or less the same end. So there's a lot of different ways of defining a tree decision or otherwise, but graph theory has a really great way of defining it, and defines decision trees as a directed acyclic graph. Graph theory is sort of like a area of study in mathematics if you're unfamiliar. So these are the main kind of rules or definitions. I forget, I can't highlight this. In graph theory, so there's one root node with no incoming edges. So that's like, imagine a tree with a node, and there's always like the one like initial node at the beginning. It doesn't have anything else coming into it. You have interior nodes always only have one input, and they have 2 or more outputs or classifications that they're classifying, right? And you have your leaf or terminal nodes that have no output, right? So those are your kind of main pillars, or the main like characteristics that you're looking for to make something like truly a directed acyclic graph or decision tree as defined by graph theory. You have a few different algorithms, as I mentioned previously, for to grow a tree with. You have ID3 trees, which is what we're really talking about when we talk about decision trees specifically. And then we have CART trees, which CART stands for classification and regression trees. So they use a little bit of a different kind of math under the hood to achieve what they're achieving, but it's all sort of, the goal is to achieve more or less the same thing. So ID3 or decision trees use some type of criterion, which is say entropy or information gain, as you see here, and you can see the calculus on those. If you're watching this video like with programming for data science in mind, I wouldn't worry a whole lot about the calculus here, which is something I'm like learning to appreciate more and more. It's helpful to be able to read this and like write code based off it, but you don't necessarily need to be able to prove it like by hand, right? Or like write a proof. So anyway, decision trees use some criterion to split the data points, and in any given node, it splits them up into like one or the other classification. And so it might do that using like entropy, which is like, say, basically a fancy way of saying like you have these two groups that it's been split into. It's not going to be perfect, right? There's going to be some group B elements in group A, right? And some group A elements in group B. But how much or how little that occurs is basically entropy. And so that's one criterion. You can use information gain, which information gain is basically like a way to quantify, describe quantifiably entropy. You can see that the function for entropy is, that should be a lowercase s. The function for entropy is like within the formula for information gain. So we're not going to get into like the reasons why you would use entropy or information gain or some other criterion, but just note that when you're writing your code and there is some parameter criterion where you can pass in a few different types of criterion depending on what you want to use. And that's going to get like really like hyper specific to your use case, like which one's more appropriate, right? CART trees, or classification and regression algorithms, use regression to make their splits, right? So basically, with CART algorithms, they're using mean squared error, or mean squared error as the criterion at each node. And this image right here is kind of an example of what a CART tree would look like when it's interpolated into a vector space, or a plot, if you will. So you can see like the partitions is where our CART tree sort of made its splits, as opposed to like an actual tree like of nodes, which we'll see in a little bit. So regardless of whether you're doing decision trees or regression trees, there's different ways that you can tune these models, just like you can with all the models that we've seen before. We've talked a little bit about hyperparameter tuning with, wow, I'm blanking. Whatever it was I talked about in the last video. There was some hyperparameter tuning. Man, what was that? It was confusion matrices and logistic regression and that sort of thing. I know it was logistic regression, but I was trying to remember what we were using our hyperparameter tuning for. Anyway, so as you can see, we have a root node, we have our leaf or terminal nodes, and we have our internal nodes, which only have one input on each of them and multiple outputs on the others. And our root node has no input, right? So there's a few different, when we talk about hyperparameter, we're really talking about the features of like the graph itself and not the parameters like in the data itself that we're passing in, which can easily be understood as like the columns in your spreadsheet, right? So like max depth. So this is like one level, and then we have level 2 and level 3. And you can imagine if these weren't leaf nodes and there was like more interior nodes right here, and this could go on forever, theoretically, right? But the problem is if you go too deep, then that can overfit your model, where basically with your training data, this graph is going to have a leaf node for every single individual data point if you go deep enough. And that's not going to generalize very well to unseen data, right? Because the model's been trained like so specifically to just the data that it's seen, that you're going to get overfitting. I don't want to ramble on too much about that. So then the minimum sample split and the minimum samples to make a leaf node. So that's basically parameterizing or dictating. Your minimum samples split is the minimum amount of samples that you need in a given node in order to split it into further nodes, right? Since we can see that this goes directly into leaf nodes, it has some amount of samples available to do that, but either of these nodes don't have whatever that value is, and so they can't be split any further, so they simply become leaf nodes. Minimum samples to make a leaf node is kind of similar, but it's a little different. So imagine like we're inside this node right now, and we only have so many samples, but we need, we have like 10 samples, but we need 15 to split. And so if we had 15, we could go like 10 and 5 here, right? Let's say that's our minimum sample split is 15, and we have 15, so it goes like 10 and 5. Right, but if we only have 10, then this actually would become a leaf node. Versus minimum samples to make a leaf node is, let's say we need at least 10 samples per leaf node, right? So we only have 15 in the interior node here. So even if we satisfy our minimum samples to make a split, we're not satisfying minimum samples to make a leaf node, because 15 can't be split into 10 and 10, right? So same but different, right? Basically, it's determining what's the minimum samples like within a node to allow it to split, and like regardless of what the amount becomes in the successive nodes. And minimum samples to make a leaf node is assuming we do split this, what's the minimum amount of samples that we have to have in each one of these nodes. So if it's 5 and we only have 9, we can't split, but if we have 10 in here, then we can't split. So little confusing when I first read it, but once I like thought through it, it's not that complicated at the end of the day. You just have to be kind of careful about the words that you use when you talk about it. You don't want to like mix up your terms too much, right? So now with the rest of this, I'm going to collapse these a bit, and we're just going to go over some example code. So we have some example code here. This is like, do not copy and paste this and expect it to run. I've kind of like cherry picked like the most important components. We're going to go through the decision tree classifier with scikit-learn, as well as the cart tree classification with scikit-learn. So we're importing our stuff here, pandas as usual. We're importing from the model trains test split from the model selection module to do our train test split on our data, and we're importing decision tree classifier from the sklearn.tree module. We import our data, we split it into our target and our predictor variables, do a train test split. You've probably seen this before if you've done any amount of data science or watched my channel very much. We're instantiating our classifier object, right? And you can see I talked a little bit about the criterion here. We're using entropy as our criterion, and the random state here is just for reproducibility. We're fitting our data to the model object, calculating our accuracy score, calculating our ROC curve, or our false positive rate, true positive rate, and thresholds for our ROC curve function, calculating the area under the curve. We've seen that was last video, I think, with confusion matrices and RC curves and all that. So now to prune the tree. What that basically means is we're looking at our hyperparameters. Whoops. And we're deciding like what the optimal values for each of these things is. So this is just an example of one of those, but we'll start with max depth. We're creating here with the linspace function basically a list of values to try out, right? So we're creating a for loop where we're instantiating the decision tree object, fitting the data to it, making prediction with it, calculating our ROC curve and our area under the curve, and we're appending that to the list for our training results. We're repeating the same process with our test sample and appending that to our test results. And then here we're plotting how train results and test results sort of change as we change the max depth criterion. So you can see here, max depth equals I. So for I and max depth, that's for every value in this, what's essentially a list of values. We're going to do this whole operation, and we're going to do this whole operation trying what each value of I is. So that's a great example of whenever you see the sigma, the summation value in like your calculus notation, that's basically what summation is talking about, what I'm doing with I here in the for loop. And the random state equals seed. In this notebook, we just set like a integer to the variable seed, and so that way I only had to write seed and I had to remember what the integer was every time. So you would repeat the same process for max depth, minimum sample split, and minimum leaf samples. And you would get the optimum values for each of those, and hopefully eventually figure out you would tune your model, right, by finding the optimum values for each of your hyperparameters. It's important to note these are only 3 of like all the hyperparameters that exist. There's a lot more, but the principle still sort of stays the same. So that's how you do that for max depth with a decision tree classifier. Again, you would repeat this process with your minimum samples for a split and minimum samples per leaf. The cart tree classification, as far as the code goes, is like pretty similar. We're just importing a different object from our tree module, this decision tree regressor. We're importing mean absolute error and mean squared error because we're doing regression now, so we need to kind of use those values. We're importing our data, declaring our predictor and our target, train test split, instantiate our regressor object, make our predictions, and we're going to calculate our mean absolute error, mean squared error, and root mean squared error for those predictions. Now we start pruning the tree. Again, this is just doing it for one hyperparameter. In practice, you would do this for multiple hyperparameters, more than likely. You can see now I have random state as 45, so all this code was sort of like cherry picked from different notebooks. But now we're like working on our minimum samples split parameter, so that's like the minimum samples that you need to make a split, not the minimum samples that you need to make a leaf. So just keep that in mind. Similar method here, only instead of like looking at just like our train and our test results, we're actually looking at our mean squared error results and our R squared results and how those change as we change the minimum sample split. So that's ultimately going to impact like how many total nodes there are like in the tree, right? And minimum sample leaf is going to also have that same effect. It's just going to achieve it in a different way. So it's going to actually affect. The difference is going to be like between minimum sample split and minimum sample leaf. They're not going to produce necessarily the exact same amount of nodes in each tree, but they both affect how many total nodes there are in the tree. If they do create the same amount of nodes, it's probably mostly chance than anything else. And they're also going to affect which exact data points or observations actually end up in which leaf. But they're going to go about that in different ways. So the same observation might get classified the same way using both, depending on either hyperparameter, but it might end up in like a different leaf for each hyperparameter. Because different leaves, you might have like 4 or 5 leaves that like are pointing to like the same classification, right? So anyway, little soapbox. Again, we're using a for loop and we're going through like all the possible values for our minimum sample split, and then we're looking at our graph here, and this is just showing R squared. There's another graph for mean squared error results that I didn't include here. And you're going to find what you're basically looking for with these graphs is like, this is a really great example. Once we go past, looks like 21 or 2 for our tree depth, there's no, both these parameters stabilize. And so there's really like no new learning going on like after that point. So that's like one thing you would look at. You can also see that the area under our curve with our training data consistently increases with tree depth. It doesn't change a whole lot. So that's something you would like look into further. And so you can see we have like kind of like a consistent decrease here until we get to about 8 and things like start drastically decreasing. Anyway, you would find like the optimum values for each of these hyperparameters by iterating through various possible values for each of those parameters. You do that for multiple hyperparameters, and eventually you would sort of prune your tree, and the result is going to be, it's going to be have more or less nodes total, more or less leaf nodes, and greater or lesser depth than whatever your baseline or like vanilla model is. So that's kind of like a broad workflow and some example code that you would run into when you're doing classification with decision or regression trees. And that is pretty much everything I have for the vlog today. If you're watching this video, I hope you enjoyed it. Hope you got something out of it. This series isn't really meant to be educational so much as me practicing, practicing what I'm learning. I think it's helpful to, you learn a lot about what you don't know from trying to explain like what you do know, right? And so this is a good exercise for me in that regard. That said, I know these aren't like super great, entertaining quality videos, but if you are watching this, I really appreciate it. If you could leave a like, you can subscribe if you want to see more of this. And if you're curious about Flatiron School, what it has to offer, I'll have the link in the description down there, so be sure to check that out. And of course, if you want to connect with me on LinkedIn, I'm going to have the link down there. And if you would like to sort of scroll through and peruse my GitHub for Flatiron or like any other repo that I have on there, it's public. Link's going to be there to my GitHub too, so feel free to check that out. And yeah, so until next time, oh shit. Bro. How long have I been without a camera? All right, well, I don't feel like re-recording this whole video. So, and that's, my face isn't really what's important either. What's important is what's on the screen here in front of you. I just now noticed that because, wow, technical difficulties right at the finish line. Wow, I should really lotion my hands. Okay, sorry about that. But like I said, it doesn't really matter like my face, what's going on. It really matters is what's going on in the video. So, yeah. A lot of things I'm learning about like the technical aspect of the production aspect rather of this YouTube stuff. So anyway, hope you enjoyed the video. Hope you got something out of it. Be sure to check out Flatiron School if you're considering a career in data science. And until next time, keep on learning, keep on coding. I'll see you later.